for attending the 2023 Speaker Series for the SRHacks Hackathon. We're happy to have you all here. And before we get started, I just want to do a couple of house cleaning, touch on a couple of house cleaning items. And that's just to go over a couple of the upcoming deadlines, especially today being the last day to register. So if you have a couple of friends, or if you're in a team and some of your team members have not registered, please make sure to have them register to the event. And also the project submissions will be available next week, but you have until April 22nd to submit your final project. In terms of the announcement for who the top 5 finalists will be, this will be announced on May 1st. And also then stay tuned for the finalist event that will occur May 13th, which will be an in-person event at the UFT campus. So if you happen to be around in the area for the Science Rendezvous Festival, come on by and check out some of the projects. So to get us started, our first speaker is Danielle Tchao. She's an engineer and graduate from the University of Toronto, who spent 10 years working as a systems engineer at MDA. And her work regarded the integration and testing of Dexter, a 2-armed robot that was launched in 2008 and has been part of the mobile servicing system of the International Space Station ever since. And following her experience as an engineer, she's also explored several entrepreneurial endeavors and is now a research coordinator at Open Lab at the University Health Network. So to tell us more about her journey, please help me welcome Danielle.
Hello. You want me to start sharing?
Yep, you can go ahead and share your screen.
Okay, thank you, Eduardo, for inviting me to talk today. As Eduardo said, my name is Danielle Tchao, and I'm happy to be invited here today to talk to you about my experience working as a systems engineer in the aerospace industry. I spent 10 years working with MDA, which is a company that I'll talk to in the future slides. You may have heard also recently announced Canadian astronaut Jeremy Hansen being announced for the next mission to the moon. So MDA is back in the news for helping out with this Artemis program. So let's sort of start by reviewing where have humans or spacecrafts even been? Where have we visited in the solar system or in the galaxy? We have actually explored quite a number of different places, including all of the planets in our solar system. Sorry, this is in slideshow mode. All of the planets in our solar system, including Pluto. I know some people still count Pluto as part of our solar system, and some people say, well, it's not one of the big planets anymore, it's a dwarf planet, but I include it. So we have here a list of some of the important missions that have been to the different planets, and we also include missions to, we've had missions to the asteroid, humans on the moon. We have a deep impact mission that went to explore a comet to find out what the composition of the comets are and understand whether or not comets contributed to the water that we find in the oceans on Earth. We had a mission to Mars with sending the Curiosity rover 2 years ago to explore the Jezero crater. And we've also sent even a spacecraft to the sun called the Solar Probe. So that was launched in 2018 and is expected to arrive there in about 2 years, 2025. So even with the Solar Probe, engineers had to design it with a thermal shield in order to protect it up to about 1,300 degrees Celsius, because the hottest lava on Earth is even 700 to 1,200 degrees Celsius. But this probe has to be protected for trying to study the sun. And it'll only actually get to the outer corona of the sun to do some of its exploration, because the surface of the sun is even higher. It's about 5,600 degrees Celsius. So eventually the spacecraft will be burned up after it hopefully takes some pictures and send some data back so we can explore the sun. I have a slide here about the moon, just because the moon will be a topic that's going to be in the news quite a bit over the next few years. We've had 6 missions to the moon where humans have actually set foot on the moon. The first mission being Apollo 11. That was in 1969, so about 54 years ago, Neil Armstrong and Buzz Aldrin landed on the moon. And I have a picture of showing where the different missions landed. So we have Apollo 11, 12, 14, 15, 16, and 17. And so you can see that Apollo 13 is missing here. And some of you might already know and maybe have watched the movie even for Apollo 13, which is a mission where 2 days into the mission, they had to abort the landing because of an oxygen tank failure. So instead of landing on the moon, they actually had to use the moon's gravity as a slingshot to return the astronauts safely back to Earth. So they never made it to the moon, which is why you don't see number 13 on the moon here. So they started landing on the moon in 1969, and 3 years later was the last mission already, Apollo 17. And that was because the cost of going to the moon was so astronomical that eventually they ran out of funding for the program. So humans have not been back since. However, just as recently as last week, we heard that they announced the crew for the Artemis mission. So the Artemis program is another program returning humans to the moon. And just a little fun side note is that Artemis is actually the name of the goddess of the moon, which is the twin sister for Apollo. So the previous missions were Apollo, and these ones are now called Artemis. And on this mission, it will include a Canadian astronaut, Jeremy Hansen. So he'll be one of the 4 members who will be headed to the moon on Artemis 2, which is next year. That mission will just orbit the moon, and then it'll prepare for the 3rd mission, which is going to land astronauts on the moon. So this is just a rough outline of what the 5 missions are for the Artemis program. The first one actually happened last year in November, which was the flyby mission to the moon. No astronauts were on board. Artemis 2, that's where Jeremy Hansen is going to be part of the crew. That's targeted for next November, where the astronauts will orbit the moon with the Orion spacecraft and return. And then Artemis 3 will be the following year, where we will land 2 astronauts onto the moon, which will be quite exciting. I think many people will be watching that. It's been over 50 years since that happened. Artemis 4 will be in 2028, where they begin assembly of the Lunar Gateway Space Station, which I'll talk about in a few slides. And then Artemis 5 is a big one for Canada, just because we'll be a part of delivering robotics to the Lunar Gateway. So we will be delivering Canadarm3, which is a set of robotic arms to help with repairs and maintaining this new space station that is being designed to orbit the moon. So you might wonder how it is that we're going to do all of this. We're building a space station, we're building robotics, we're trying to have it all maintained in space autonomously in some cases. Well, we can build upon experience from the International Space Station. The International Space Station is a collaboration with many countries. And the first crew went up in 2000. And I think there's been about 266 people who have visited the space station. That's including over 20 different countries. So we've had lots of experience taking astronauts to the space station, launching equipment to help build the space station and help repair it. The space station is actually in lower Earth orbit. So that would be anything below 2,000 kilometers above the Earth's surface. So the space station orbits the Earth. It's about 400 kilometers above the Earth. And our main contribution to the space station was the development of the Canadarm. So I worked for 10 years with MDA, or at the time when I worked with them, they were called MD Robotics. They were previously known as Spar Aerospace. So they built a set of robotic arms to help with maintaining the space station and delivering cargo to the space station. So we had shuttle arms called Canadarm. They were part of the shuttles that flew to the space station. They would bring cargo, bring payloads, bring resupplying resources back to the space station. And the arm would be attached from the shoulder to the shuttle. And once it docked to the space station, then the arm could extend and bring out payloads such as the Hubble telescope, bring important supplies back to the station. Now, they figured that the shuttle arms were quite important. They wanted to actually have a more permanent arm that would stay on the space station to help with repairs. So that was when MDA was asked to build a Canadarm2. So I was lucky enough when I was studying engineering at U of T, at the University of Toronto, to spend about 16 months working with MDA at an internship. And I did some of the testing with Canadarm2, some of the simulations. And then once I graduated from U of T, I went back there to work for 10 years. Now, by the time I graduated and went back, Canadarm2 had already been launched. That was launched in 2001. And it was actually assembled by Canadian astronaut Chris Hadfield up in space. So he was the first Canadian astronaut to walk in space, and he was the first Canadian astronaut to be a commander of the International Space Station. So by the time I came back, it was already launched, but of course we have spare parts for the Canadarm. So this robotic arm is about 17 meters in length, and it can move about the International Space Station kind of like an inchworm. So either end of the Canadarm can be used as the base, and either end can be used as the hand. And the hand is sort of, it's made up of different mechanisms in order to help it capture payloads, help it move electronic units in the space station. If you need to do a repair, you can use it to grab something that's failed, move it to a different location to store it, and then put a replacement unit in it. And it does it by using what's called these latching end effectors that you see in the bottom corner of the slide. So those are what are known as the hands. So there's a hand on either end, actually. There's hands sort of on the what would be called the wrist of the arm, but there's also a hand on the other end where you would normally have the shoulder. And that way, this Canadarm can walk from one place on the base, like an inchworm, to another location to relocate itself for whatever repair it needs to do. So we have some of these spare parts on the ground, just in case there's ever a problem with the robotics. We can launch it and then switch out the component using an astronaut spacewalk. So when I came back to MDA, I did a bunch of testing for the latching end effector. And we can do testing at this laboratory in Ottawa called the David Florida Laboratories. And I pulled up a picture here from my testing days way back in 2005. So what we do is we send flight hardware to this laboratory, David Florida Laboratories in Ottawa, and they have a series of chambers, thermal vacuum chambers that can simulate the environment in space. So for example, the chamber can go from minus 150 degrees Celsius to plus 150 degrees Celsius. And what we want to see is whether the hardware, and mainly the electronics, whether it can operate properly in these environments, so that when we launch a spare part to replace a failed unit in space, then we know that it is working properly. So in this picture right here, it's kind of hard to tell because there's so much equipment, but anything that's in black is actually part of a test rig. So we have sensors and we have cameras and we have things to measure data, so that when we're operating the latching end effector, which is actually just sort of the shiny bit that's encased inside the test rig, then we can measure to know whether it's performing properly. And we can operate everything from a computer on the side. So the test rig will slide out. We can move it into the test chamber, close the door, and then simulate the environment that we want to. So whether it's something very cold or very hot. Now, aside from testing spare units for the Canadarm, I spent quite a number of years working on a two-armed robot called Dexter. So Dexter, you can actually see, is featured on our Canadian $5 bill. So if you ever have some time to take one out and take a good look, I tried to pull up a picture that kind of matched the same orientation as the bill. So you see the Canadarm2 from the space station, and it's holding this robot Dexter that's on the tip. So the Dexter, it's not what you might think a robot looks like, but this is the body. Can you see my cursor, Eduardo? Yeah, okay. So the body here is about 3.5 meters long. And then it has these two arms that are also approximately 3.5 meters long. And each of the arms have 3 joints at the shoulder, an elbow joint, 3 joints at the wrist. And that allows this robot to move quite a bit and sort of handle getting into tight spots on the space station, because the main purpose of using Dexter is to replace parts on the space station so that we don't have to send astronauts out there all the time. Sending astronauts out would require a lot of planning And there's also limited amounts of time that astronauts can spend on a spacewalk due to, oxygen and resources and sort of their own level of fatigues. So we use the robots whenever we can. And the Canadarm, both the Canadarm and Dexter can be controlled either by the astronaut crew that's on the space station, or it can even be controlled from the ground. So they can send commands from Houston, from the Johnson Space Center in Houston, to command both of these robots, even while the astronauts are asleep. So this is an extra way for us to maintain the space station without relying just strictly on the astronauts and their spacewalks. And Dexter can have, Dexter actually has sort of like a head and a bottom, but either end really could be used as the base. So right here we have the Canadarm holding on to Dexter on one end, but then you can move Dexter over to another location on the base, and then you put them down on the other side. You would power up from the other side and then remove power from the Canadarm. I wanted to just show a few photos from our facility at MDA in Brampton, Ontario. So this is the clean room, or a large task area where we can test some of the flight hardware. So what you see in sort of yellow and orange are these huge test rigs, because what we need to do is support the robotics with a bunch of pulleys and counterbalances. If you imagine operating these robotics in space, it can move large structures, large, very heavy structures, very easily because of microgravity, because you don't have the same weight, the gravity that you have on Earth. But if you were trying to move those types of payloads here on Earth, that would put a lot of strain on the robotics. What we want to do is simulate the kind of stresses and loads that you would find in space, and use those loads here for testing so that we can generate all of this data, understanding the performance of the motors, of the joints, of the sensors, so that we can compare it later on with how it's going to perform in space. If we don't use counterbalances, for example, and you can imagine a motor struggling to lift something that's very heavy on Earth, and then you wonder whether it's performing properly in space. Well, you can't really compare that data. You need to make sure that you're under the right test conditions. Otherwise, you wouldn't know whether comparing something from space to something into very different conditions on Earth would match, and you wouldn't know whether there was an actual issue with the motor. So we have a bunch of these test rigs with counterbalances so that it helps to move some of the joints as it's trying to go through some of its motion. This is just a funny picture I have testing Dexter with one of my friends who was a coworker, and we had an open house where we were invited to bring along family members. So here's a photo that I included with my parents coming to see the task area and take a look at the robot while we were doing integration and test. And here is a photo from the launch of Dexter in 2008. So there were 4 of us that were sent down from MDA to the Johnson Space Center to support that flight. Dexter was launched in 2008 in March, and it was pretty exciting. It was the first time we would see our robot that we worked on for many years being launched and assembled. So if you can imagine, we assemble everything on the ground, we test to make sure that it's okay. But before launch, we disassemble the robot so that we can put it into these pallets and secure it properly so that it doesn't get damaged during the launch, because there's lots of vibration during launch. So we need to take the arms apart from the body, we secure it in place, we launch it, and then up in space, the astronauts will come out and they will reassemble the robot. Now, before Dexter can be used for any real mission, it needs to go through a whole suite of checkouts to make sure that nothing was damaged during the launch and nothing was damaged during the reassembly. So we perform a whole suite of tests, and this is where we can compare it with the data that we used on the ground to test it, to see whether, does the motor current look proper? Is it moving at the right speed? Is it comparing, can we compare it to something that we did on the ground where it was moving this sort of payload and identify whether there's now something wrong with it because the motor current is too high or it's not moving as fast as we expected? So this is why we want to try and simulate the conditions on the ground so that we know we can compare it to something once it's in space and then say yes or no, it's ready to perform a mission. So in black and white is this photo that we took in the flight control room. So this is the room where we don't normally get to go as engineers. This is the room where Capcom relays messages to the astronauts. So the communication goes from the astronauts to Capcom, and from Capcom, it goes down to the robotics operators, or robo. So this guy on the left here with the sort of frowning a little bit, I think maybe he wasn't sure that we were going to be allowed to be in the flight control room because we were the backup engineers, but there was an actual issue that we had to help troubleshoot. So we were allowed to come in, and eventually we snuck in a little Canadian flag just to take advantage of that opportunity. Normally we're outside in another room. So if you see on the left picture at the top, I'm analyzing data to make sure that everything's running properly during one of the tests. Now, we wanted to really go and see this launch from the Kennedy Space Center in Florida. Unfortunately, they didn't allow us to do that. So there's a 2-day window where the hardware gets launched, and then 2 days later, the space shuttle will get ready to dock with the station, and then you can unload the hardware. So we had sort of 2 days to get to Kennedy Space Center, watch the launch, and then go down to Houston. But they thought maybe that timeline was a little too tight. They didn't want anything to go wrong with the crew that was going to help with supporting this mission. So we were not allowed to go down. Now, the following year, I was lucky enough to be sent down as media to watch a launch. That was, it had Julie Payette, which is another Canadian astronaut who was also our Governor General up to recently, up to last year. So this is a picture of me down at the Kennedy Space Center where I was able to look at the shuttle on the launch pad, and I was able to meet Chris Hadfield, who, again, I mentioned earlier, he was the first Canadian astronaut to walk in space and the first Canadian astronaut to command the space station. Unfortunately, at that time, we didn't have, everyone's smartphones that you can quickly check to see whether your photo came out properly. So someone took this photo without flash, and it's a little blurry, but you can make out that it is Chris Hadfield here. Unfortunately for this launch now, I was all ready to see this. The weather conditions were perfect. We walked out the next morning to get ready with the astronauts going out to the shuttle at about 2 or 3 in the morning to get ready for this mission. And then it was delayed because of a mechanical failure. So that was my second chance of going to see a mission, but unfortunately that one was delayed. I didn't get to watch a shuttle launch until a few years later, when it was about, I think it was the third last shuttle launch before the shuttles were retired. So I did eventually get down there, but it took a while, a few tries. And this is just a shot of the Canadian Space Agency. So if we are supporting a mission where our hardware is being launched into space, then we will send some of our engineers down to the Johnson Space Center. But for other regular operations that use the Canadarm or Dexter for a mission, then we often have engineers out to the Canadian Space Agency, and then we can support the flight from there as well. So you can sort of see what that looks like. To be honest, I took out this picture, and when I was back there, it wasn't quite so cool looking, but I'm glad to see that it is advanced. There's a stall. I was going to show just a part of this video that explains a little bit more about how Dexter operates in space. And hopefully the audio is okay. There's a delay though. Here we go.
Today we'll look at a very particular robot that spends most of its time in space. Robots are used widely in space exploration. Most of you know those such as the Mars rovers, but there is one that has been in service for over 15 years now. And it is even closer than you think. This robot here is Dexter, also known as the Special Purpose Dexterous Manipulator. Built by MDA Limited, a Canadian space tech company, it was launched on the Space Shuttle Endeavour in March 2008 on the mission STS-123. Once in space, it was latched onto the International Space Station at one of its grapple fixtures. Costing more than $200 million, this robot closely resembles science fiction space robots, but it is fair to say that this real-life machine is an even more remarkable feat of engineering. Dexter consists of 2 dexterous, 3.5 meters arms which are attached to a torso-like base. Each arm comprises 7 joints, namely the elbow, shoulder, and wrist joints similar to a human arm. What's amazing is that this whole setup weighs about 1.7 tons and pivots about itself, so you can have an idea already of how flexible of a machine it is. What's even more fascinating is that on top of that, It is fully mobile. The powerful Canadarm 2 can grasp Dexter and position it around the ISS worksites, also known as the orbital replacement units. Being the most sophisticated space robot ever made, Dexter has the ability to perform routine tasks, which would otherwise require astronauts to go on spacewalks that demand long preparation times and have a certain risk element associated with them. Each of its 5 links can not only move up, down, and sideways, but also rotate about its own axis. To ensure the proper motions, inside each link is a camera for visual feedback. The hands at the end are packed with force-sensitive sensors, allowing them to have a sense of touch equivalent to that of humans, and that can even compensate for payloads. Having a precision of a few millimeters, Dexter can work on both ends of the spectrum, as it is also strong enough to manipulate equipment the size of an adult human. Further tools at the end effector include a motorized wrench and a retractable connector to supply power and data. One very interesting fact is that the robotic manipulator assists astronauts even while they are sleeping. This is because it is operated entirely from ground control teams at NASA and the Canadian Space Agency headquarters located in Quebec. Let's now take a look at the main tasks of Dexter. These include maintenance work for the ISS and also acquiring payloads from transport modules such as the SpaceX Dragon capsule, which so far has done 34 visits to the space station. Dexter's first official assignment, which took place in February 2011, was in fact to unpack the Japanese HTV cargo module, and get this, it was done entirely while the crew aboard was sleeping.
Okay, so I'm going to pause it right there. That gives you an idea of what Dexter is capable of, and it is used quite often for doing repairs, replacements, and helping to even explore ways that we can maintain the space station in ways that we hadn't originally imagined. For example, helping to refuel satellites that have been left in space and perhaps normally would run out of fuel and not be used anymore. Dexter has a set of different tools it's trying out in order to try and open the caps, for example, on the satellite so that we can do refueling missions and maybe extend the lives of these satellites.
Today we'll look at a very particular robot that spends...
Sorry about that. I wanted to talk a little bit about NeuroArm. So for NeuroArm, while we were developing all of these robotics for space, one of the neurosurgeons at the University of Calgary, he was interested in how our robotics could be used to help with brain surgery. So 2008 was quite an exciting year for MDA. So we had Dexter being launched in March, but also it was the first surgery using this NeuroArm robotic arm that was developed by MDA in collaboration with this doctor at the University of Calgary. So what he envisioned was having this robot operate in an MRI. So an MRI produces these very detailed images. So in this case, he's doing brain surgery, and he can look at these references for images of where a tumor might be in the brain. And he wants to operate on the tumor while being able to see these images at the same time to make sure that he is not getting close to any structures that could cause any risk or harm to the patient, and that he's able to extract all of the tumor that is visible in the images. The challenge with developing a robot that would work near an MRI is that you need to use non-magnetic materials. So you can't use something like steel. You have to come up with different materials and components, and also make sure that the electronics that you use don't interfere with the images that are being produced by the MRI. So it was a big challenge for MDA to help develop this tool, but it was an exciting new field to explore how robotics could be used in medicine. So this NeuroArm has actually been used in over 80 patients already. And the cool thing about it is that it allows the surgeon to be in another room. Possibly you could do this with the surgeon in another hospital, in another city. So if you can imagine a city where someone needs some sort of rare, difficult surgery that not every surgeon has the skills for, then you might be able to take advantage of neurosurgeons who are in a different city to help with doing the operation. So there's a picture at the bottom with Dr. Garnett Sutherland. He's in a different room and he's using different like hand controllers that are finely tuned to the robot performing the surgery on the other end. So for example, if there's a difference in sensing the types of tissue that are in the brain, some from healthy tissue to a tumor, you might feel that there's more resistance or the sort of the feel of the tissue is different. It translates that force back to surgeon. So it feels that kind of difference and it knows that here I am operating on healthy tissue, here I am operating on something that should probably be removed. There's a capability of programming the workstation so that if you want to do very, very precise motions at the tip of the robot tool, if you only want to make an incision that's maybe just a few millimeters, well, you can filter it so that on the operator end, he might be able to move quite a large distance with his hand, a few centimeters, and that scales down to very precise motion at the tip of the tools. And that way he can make very fine incisions and not worry about maybe shaking of his hands. Perhaps the surgery is taking many hours because many of these surgeries are quite complicated and you're tired, and the workstation can filter out these tremors in the surgeon's hands. And you can also set up what are called no-go zones. So there might be parts of the brain, obviously, that you do not want to enter or accidentally, put your tool near, because it could cause brain damage or any sort of injury that is not reparable for the patient. And so you can design these sort of planes or walls or barriers that are virtual, and you can say that no matter what I do at the workstation end, that the tool will not cross over these barriers, and you can set those up to safely make a boundary for your robot. And I'll share here just also a video of the NeuroArm very quickly.
Attached to the outside of the International Space Station is a robotic arm called Canadarm2. It's made of cutting-edge carbon fiber and is powerful enough to lift an arriving supply rocket, yet agile enough to change a circuit breaker, thanks to a robotic attachment called Dextra. Using a complex series of joints, this unique robot has more range of movement than a human arm. It's an innovation that caught the eye of pioneering brain surgeon Dr. Garnett Sutherland.
When we saw that robot for the International Space Station, we knew that a robot could be built that could work inside a neurosurgical operating room.
Dr. Sutherland worked with the engineers who created Canadarm2 and Dextra to build a one-off robot for his operating room. He thinks this could be the future of brain surgery.
Robotics has the tremendous advantage of merging the precision and accuracy of a machine with the best of what a surgeon can deliver during surgery.
Jamal Halat is 33 years old, and this robot could save his life. Jamal suffers seizures when abnormal blood vessels bleed into his brain.
I was at work and I had a severe headache. 3 days later, I woke up and I just didn't know what happened.
Jamal's traumatic seizures could be repaired with traditional surgery, but that kind could also harm his healthy brain and impair his speech. Dr. Sutherland believes surgery using his robot is the safest option.
Combining that precision and accuracy with the movement that the surgeon can deliver provides Jamal with the best possible outcome from his surgery.
Okay, so that was just a little clip showing the NeuroArm. And again, for MDA, they have been exploring a lot of robotics for space, but we've also now explored how we can use robotics in medical field or even in a nuclear as well. So let's just return our attention now back to space for the last part of this presentation. Let's see. Feel like
Attached to the outside of the International Space Station is a robotic arm.
It is failing here. Batteries. Here we go. Okay, let's go back to looking at space and exploration. So in the very beginning of the presentation, I mentioned the Lunar Gateway Space Station, and this is going to be part of the Artemis program. So the Lunar Gateway Space Station is a smaller space station than the International Space Station. It's meant to orbit the moon rather than Earth. So it'll be much further away from Earth than the ISS. So it'll be 1,000 times further. It'll be 400,000 kilometers away from Earth, which has quite a number of challenges with communication, because you can imagine at that distance, there's quite a lot of delay for sending up commands and then responses coming back from the space station. It's also not meant for astronauts to live in continuously the way that the International Space Station is. For the ISS, there's always a crew there, and then you send up a new crew to take over and you relieve the old crew to come back. But for this Lunar Gateway, astronauts can maybe stay up there for 3 months at a time, but the main purpose of this space station is for using it as a communications hub and to do some research, but not to have a crew there living all the time, which means that any repairs and maintenance that have to be done on the space station need to be done without humans always monitoring it. So MDA was contracted to build Canadarm3. It's actually a set of these two arms, a larger arm and a smaller arm, to perform maintenance tasks the same way that they do it on the International Space Station. These ones are a little bit smaller than the Canadarm2, and they also need to be outfitted with like a number of more advanced sensors for doing autonomous motion. If you can imagine, there are no astronauts up there to help control the robots most of the time. And there are these delays that happen from sending telemetry or commands from the ground up to the robots. So it has to perform a lot of these decision-making analysis all by itself. So in order to maintain the space station, we're relying on these robots to be programmed in such a way that it can make decisions without continuous input from humans.
Hi, my name is Tim Kopra. I'm the MDA Vice President for Robotics and Space Operations. MDA has been the premier Canadian company when it comes to space. So if you look at the Canadarm that's been on Space Shuttle, Canadarm2 that's still on Space Station, this new Canadarm is different in that it has to operate autonomously during certain periods of time.
So if you can imagine leaving your kids at home for a week, not calling them or emailing them or anything, and still expecting them to get all their chores done, that's essentially what we're doing with Canadarm3.
We have a second arm, a smaller arm, that maintains the big arm. And what that does for us is minimize the number of spacewalks that are required to maintain the Lunar Gateway.
There's a small dexterous arm, there's a tool caddy and a whole suite of tools that enable us to perform all of the various tasks that need to be done up on the gateway. We perform free flyer captures of visiting vehicles, a whole host of functions that the robotic system has to perform.
What excites me is the opportunity to work on things that are literally out of this world.
Before this, I served as an astronaut, and I had lots of opportunities to actually work with and operate the hardware that we build here. So to connect my previous life when I was an operator to this opportunity for us to build the next generation of robotic systems is super exciting.
And I think I have just about 2 more slides. One is just showing you a quick idea of what we imagine exploring the moon will be like with rovers, and then I will wrap up with my last slide. You're looking at different robotics that can be used to explore on the moon's surface as part of the Artemis missions. So I just want to end with my last slide. It always plays again as I move. My last slide is Mars. So why are we spending all this time focusing on going back to the moon since we've already been there 50 years ago? Well, scientists are very interested in exploring Mars and sending humans to Mars, but Mars is quite a distance away, and sending anyone there is a large commitment. So if you imagine going to dock with the new space station that's orbiting the moon, it would take about 5 days to travel there and to dock. Now, if we want to consider a mission to Mars, well, Mars and the Earth have different orbits around the sun. So at different times, they might be on opposite sides of the sun and far apart. And other times, they would be close together on the same side of the sun. Now, if you're going to be planning a mission to send a rocket with people from Earth to Mars, you're going to try and plan it where the two planets are closer together. And even then, it would take about 7 months to travel just one way to Mars. Once you get to Mars, you're going to want to conduct some science experiments, build a facility to live in, a little base, and then you need to wait for the planets to realign for a short distance to return as well. So now we have 7 months of travel each way, and you have time on the planet to do your science experiments and wait for the realignment. So a mission to Mars is easily 3 years. Now, how are we going to be able to send people to Mars and provide them with enough sort of resources and food and rocket fuel to come back? Well, we need to understand whether there's anything in Mars that we can use in order to help with that. So for example, right now the Mars rovers are looking at the Jezero crater, trying to see whether there is existence of water underneath the surface. We're going to be doing the same thing on the moon, and possibly even use any water that we get from the moon or Mars to create rocket fuel. So say you can use rocket fuel to launch your spacecraft to Mars. Well, maybe if we don't have to bring enough fuel to return, we can actually manufacture fuel there and return your spacecraft using that. Or we would use water to grow food potentially, or for hydration purposes. So there's a lot of studying that we need to do for building a base and learning how we could live on a different celestial body such as the moon before we consider, before we are realistic about sending anyone to Mars, which I think NASA has announced they would like to do in about 15 years time. So we have a lot to learn during that time, but we are excited to know that the missions to the moon are happening again, and they will start next year with sending one of the Canadian astronauts along as well. So I think I'm pretty short on time right now. I just wanted to end that. Thank you for letting me speak about this experience.
So thank you, Danielle. That was fantastic. So we are running a little bit short on time, but we do have some time for a couple of quick questions for you. So some of our students were wondering, I guess this is referring to the image that you showed of you in front of the computer, I guess troubleshooting. And how does that troubleshooting process work? Like, do you get information all the way from space about an error, and how do you go about fixing it, and what are those steps looking like?
So the funny thing is, there's a very strict protocol of who you listen to on the loops and who you get to talk to. So it's always from the astronauts to Capcom to the robotics operators that are in the flight control room. The next step would be where we were in the engineers at Houston. And then the backup would be engineers that are at the Canadian Space Agency. So you listen to everyone who's above you, and
Okay.
they only listen to whoever they talk to. So when they need your help, they will call down to you. So what you do is you hear everything that's going on. And if, for example, we were troubleshooting things where maybe there was no power. At one point, we first hooked up the robot and we weren't getting power yet. So you already know that's happening because you can hear what people are reporting. And at that moment, what you're doing is you're working as fast as possible with your colleagues who are at the Canadian Space Agency to look through all of the failure codes that you've ever had during testing to try and figure out what are the different options of how we can try and troubleshoot this. And then you would relay that message back to the robotics operators. Now, funny enough, we were troubleshooting something with the brakes, and normally you would speak to the robotics operators and they would transmit to Capcom, but there was just not enough time to do that. So they invited two of us to come into the flight control room when normally we're not allowed to be there. And we were able to talk to the flight director just directly. So that was a lot of excitement for us.
That's amazing. I mean, it sounds really stressful because I think a lot of people usually use like Google or Discord to like look up those errors, but something in the
Yeah,
space
it's like
station is
everyone's
how you
waiting
can
for
look
you to
that
make a
up.
decision. Yeah, they're waiting for you to say like, what's the next command going to be? And then I remember
Yeah, wow.
troubleshooting and then walking, they said, okay, you're just going to come with us to talk to the flight director. And in my mind, I was thinking we're going to go to like a conference room or something,
Yeah.
but of course she can't be off of the flight control room. So we walked into the flight control room and it was quite an experience to be in there because normally you wouldn't be in there.
Yeah, no, that sounds super exciting. And I guess in the same vein, some students are wondering about kind of your journey there. Like, how did you manage to become an aerospace engineer? And do you need any special training aside from your engineering degree? Like, do you have a couple of words on someone that might be interested at this stage, looking up at something like that potentially as a career?
I mean, most of my colleagues would have studied engineering in some capacity. So I studied electrical engineering through the engineering science program at U of T. And of course, we have lots of computer programmers, software developers, systems engineers. So for systems engineering, I mean, it's obviously helpful to have a lot of background in if you are doing even programming little projects right now. I think that for your hackathons, you have sort of projects where you are doing little competitions, right? So once you are involved in those types of competitions, you get a sense of how you troubleshoot, how you design, and then how you evaluate the designs to know whether or not they're good. And all of those experiences help with building your intuition to know whether or not you can look at a design and say, well, I'm not sure if this is the best way of doing it because I remember doing this project when I was younger and we had these issues and maybe we need to work around those issues for the next project that we're working on.
No, for sure. And thank you for referencing it, because that's really the goal of this whole competition for everyone here, is to get you guys used to develop those fundamentals. So once you get to where Danielle is right now, you are able to tackle any problem in space or here on Earth. Okay, thank you, Danielle, so much for attending. Right now, we'll be going into break and we'll be getting ready for our next speaker. So we'll be back in 10 minutes, everyone.
Okay, thanks so much for having me.
Okay, welcome back, everyone. Our 10-minute break is over, and then now we'll be continuing with our second speaker, who is Dr. Michael Reber. And Dr. Reber originally obtained his PhD in human genetics from the University of Deriot. I probably pronounced that wrong. Apologies. In France, and subsequently did his work as a research associate in the Salk Institute, where he then studied neuroscience. And from there, his research has been focusing on the development of the visual system, in particular, the formation of the network between the eye and the brain in normal and in eye diseases. But his work also includes creating and identifying new rehabilitation methods for visual impairment using virtual reality. And the software that he uses actually developed in Unity 3D, which is very well known as a game engine that is used to make video games. So to tell us more about this cool and strange combination of healthcare and game development, please help me welcome Dr. Michael Reber. Oh, sorry, Michael, I think you are muted.
Yes, I'm muted. Sorry. Thank you very much, Eduardo, for inviting me. I mean, I think I was there also last year or 2 years ago, and
2021. Yes.
It was a really fun experience. So I'm really glad and happy to be here with you. So I need to share my screen, correct?
Yes, I think you should be able to. You are currently the host.
How is this? It's all good?
Yep,
okay.
Looks good.
Okay, so do you see my laser pointer? All right. So should I start then?
All good to go.
Okay, all right. Well, then I'm very happy to be here with you this afternoon, and thanks for attending. It's nice weather out there, and some of us would want to prefer go out and have fun. soon, in less than 45 minutes, you will be able to go. So I'm Dr. Michael Reber, as Eduardo said. I'm a senior scientist at the Donald K. Johnson Eye Institute at the Kreml Research Institute here, University Health Network, that's right next to the Toronto Western Hospital. And I'm also a professor in the Department of Ophthalmology and Vision Science at the University of Toronto. So we are interested in using high tech and especially virtual reality to help individuals who have visual problems. And so the question is, how can we help people with vision problems using this tool that probably many of you are familiar with, or at least have heard about, or probably also tried and played around with. So the idea here is basically to help people who have vision problems, and vision problems can occur at the level of the retina. So on this picture, you have a side view of your brain and the connection of your eyes to different parts of the brain that are very important for processing visual information. So lots of people have problems in eyes, and these are due to degenerative diseases. I'll mention that a little bit earlier, but you can also have issues. Those degenerative diseases are called glaucoma, or age-related macular degeneration, also called AMD, diabetic retinopathy, but it could also be a trauma. If you have a car accident or a bike accident, and especially if you don't wear a helmet as you're biking, you can injure your face and then your eye, and also injure your brain, and that's not good. You don't want that. So problems in the eye, problems along the optic nerve, which is those wires that are basically transferring the information that is collected by the retina, and it's transferring this information to the brain. This is done through the optic nerve, which you can imagine is just like a bundle of wires, sort of. And the visual information is transferred to different brain areas. And optic nerve can be injured also through trauma, cancer, or also glaucoma. The eye disease called glaucoma affects the optic nerve. And then you can have problems in the brain itself, and particularly in brain areas that are dealing with visual information and that are processing visual information. These are mostly in the back of your head, the back of your brain, and problems or injury occur because of trauma, cancer, or also stroke, which affects this part of the brain here in the back, which is called the primary visual cortex. And what happens then is that when visual information is processed in this visual cortex, then processed visual information is sent all over the place, all over the brain, in more so-called associative area or decision-making area that help you decide what you are going to do depending on what you see. So we will be focusing, and we will talk about today, we talk about these diseases and some of those trauma, cancer, and stroke. Now imagine you have normal vision, and when you have normal vision, you can play this famous game, and everything is okay. Now, if you have visual field issues, this is what you can experience. So you have some sort of losing visual information in one side or the other of your visual field. This is called homonymous hemianopia. And this is due to a trauma or a disease in the back of your head. You can also have other type of disease. So this is homonymous hemianopsia on the other side. You can also have hemianopsia just on a quarter, or just in sort of a smaller part of your visual field, but it still affects you, your mobility, and your moving around. You can also have issues like this, which corresponds to glaucoma. Glaucoma creates this sort of shrinking of your visual field, and it's very difficult then for you to anticipate what's coming from the side. So one can easily imagine that driving, but you're not yet concerned probably by driving, but I mean, on a bicycle or playing sports can be a bit challenging for these people. if you have a macular degeneration, this is what you experience. You have this black spot in the center of your visual field here, and it's very difficult to read in this scenario. And of course, this also strongly affects your daily living and your daily activity and tasks. So what can we do? What, with the knowledge that we acquired over the years about how the visual system works, and together with the high technology that are available out there, what can we do to help these individuals who have visual problems? And again, we are going to take advantage of our knowledge of the brain on how the visual system works and how those visual information are sent once processed by these blue areas, or how these visual information are sent throughout the brain, to try to come up with ideas or methods that can help these participants. So just to give you a rough idea, this is the wiring of the visual system in the brain. It's some sort of the layout. As you can see, it's extremely complex. And there are multiple areas. So every colored rectangle here corresponds to a brain area. Basically, the eye is lying down here, and all the rest is the brain. So you can see that this is a very complex, intricate connectivity and wiring of those brain areas that are constantly exchanging information. And what can happen if you have a trauma in your brain, or if you have a neurodegenerative disease, is that part of that circuitry doesn't work, is dead, basically. So information that was supposed to transit through that area can't anymore. And so therefore, the processing of the visual information from that particular area doesn't exist anymore. And of course, this can dramatically impact the quality of the visual information and what you can get out of your visual information. You can have full damage, you can have partial damage like this, with kind of some sort of holes that are still, I would say, intact or healthy, but no information is arriving to those holes that are still healthy. So over time, those little patches of healthy tissue might die because they don't receive any information. You can have larger areas also that can be affected, and which then creates even more problems for you in terms of vision and visual field. So we rely on some sort of a concept that is not new in the field, but has been sometimes a bit ignored, I would say, is that the brain can really be considered like as a muscle. And you can train your brain. When you learn new things at school, you're basically training your brain, and you can train your brain as you train your muscles. And if you have a good coach, well, maybe you can dramatically improve, well, your physical health and your strength, but also your brain. And so we are doing this using a so-called Oculus. So this is the Oculus Quest 2. We now moved on to the Meta Pro, which is like a higher end of this type of device, which allows us to do much more recordings and much more collect much more information about how you guys, or I mean patients, are using their vision to solve different type of visual and auditory stimulation. And I'm going to show you now what we use to stimulate the patients that have low vision, or that have issues with visual fields, and what type of task they are doing. So this is typically one of the visual tasks that we are providing to our patients. So it might seem very simple for you because your vision is probably normal. You must picture that as you have a part of your visual field missing. So what's going to happen here is that one of those 8 balls is going to turn red, and then it's going to turn yellow again, and everything is going to move. And using your vision, you are basically tracking the ball that was the target. And after some time, the whole process stops. And the goal is for you to select what you believe is the target. So as I said, this seems probably very simple for you because you have normal vision. And so you have this ball now which will start moving, and it moves rather slowly. We can adapt to the speed and so on. But just imagine you have visual field problems, and this is now becoming an issue because the ball might move into the dark field and you can't see it. What if you have glaucoma? You know, your visual field is shrinking, and it's very difficult to be able to follow these balls. We can make it a little bit more challenging and put that in some sort of virtual reality, realistic environment. This is the corner of Dundas and Spadina in Toronto. And you can basically perform this visual task of tracking into a more realistic background. And again, it seems maybe easy for you, but imagine you have hemianopsia, or imagine you have glaucoma. So things are becoming much more challenging. And the point here is to have the patient doing this exercise in these many different contexts that are more and more challenging, and to see afterwards when they go to their doctor, what is happening? Can we improve their visual perception in this blind field? Can we stimulate or re-stimulate those spots of healthy areas in the brain that allow you to still perceive and see things even though you have low vision? And so to do this, we use something that you're probably also very familiar with, is Unity. And we use Unity to generate the game. And here's just an example of how we do that. And maybe you are also familiar with all those screens and processes in Unity, but this is basically what we are doing. We are coding this game in Unity, and then this is all installed on the headset. The headset is given to the participant, and the participants are actually doing the tests at home. They don't come to the hospital, which is the beauty of that approach, because one can imagine that if you have visual problems, you know, if you would have to travel or commute every day from your home to the hospital, yeah, this would be quite challenging. And sometimes you would even just stop, you know, doing this treatment, because just going from your home to the hospital is already difficult and not easy to do on a daily basis. So what we do is we provide this headset to the participant, and they take it home and they do the training at home. And because it's connected to the Wi-Fi, we collect the data, okay? And we can then improve the stimulation on a daily basis when we see that the participants are improving. For example, the speed of the targets goes faster and faster and faster, and so on and so on and so on. So we are using this guy. Here is an example of the Unity dashboard that we have in the lab. So this is on our end in the lab. We can set up all those parameters. This is how this was all coded, and you're probably familiar with this, but we have coders in the lab that are doing this job and putting everything together and making sure everything works. So the principle is this: we are in the lab, we do the coding, we generate those visual tasks for the participant. This is sent through Wi-Fi to the participant's home, where they have their Oculus Quest connected to the Wi-Fi. So basically, every features and specs of that particular training is sent through a Wi-Fi to the participant, and then the participant follow their training program. And in our case now, we are having training programs that last 4 to 6 weeks, and the participants are using this every other day for basically 15 to 20 minutes. So it's 20 minutes of target tracking and recognition, 20 minutes of target tracking and recognition every 2 days for 4 or 6 weeks. And then we collect the data directly in the lab. We have tons of data that we are receiving, and we are analyzing on a daily basis. We have some sort of artificial intelligence almost in the background running, which is calculating the optimal speed based on the performance of the participant. And then you have an algorithm that calculates this, and then everything is sent again in this loop back to the participant. And this loop is like lasting for basically 6 weeks every 2 days. When we are collecting data, the AI is basically improving the program every time, so that we really keep the participant, on the edge, that we keep challenging them, because over time you learn how to do this, you get better and better. And after becoming better, if you keep the same speed or if you keep the same difficulty, it's going to be easier and easier and easier, and you are not progressing anymore. Okay? You are not learning more. So you need to make it more challenging every time. And this is what we do. And so basically, well, when we start with a participant who have vision issues and maybe don't see much, at least in their visual field, after they went through our training for 6 weeks, what we observe is that they dramatically improved their vision. And the way you do this is you perform so-called clinical trials or clinical study, where you select a certain number of participants and you provide this tool, and they go to their home and perform the stimulation, and then they come back to the hospital after 6 weeks, and we look at their vision and how it improved. And then when you have enough participants, you can then so what we call writing results, and you publish a paper, and then you inform your peers, the doctors, but also other patients, that there is a technology available out there that can maybe help. And so this is this work was recently published in the Globe and Mail also. I mean, that was a bit advertised and explained to people the technology that we have. The people involved in this work, well, is your SRHack National, that guy over there. So Eduardo has been working in my lab, and he's the one behind those coding and programs and dashboard and so on, together with another dude, which is who's really good at this also, Pai Nazir, who used to work in my lab also, and now is some sort of consulting for my lab and working with us to keep improving these stuff. So you can see that, coding, high-tech, VR, which originally was designed more for games, is now expanding in other fields that are, I believe, really, that's the future, that this is something, it's extremely promising. And I must say that this is basically the beginning. I mean, the use of VR in medicine to help patients, and in particular in the field of vision, this is just starting. It's been around for like maybe 2 or 3 years, but because the devices are also technologically improving, we just need to keep up, because those devices are providing us with many more features. As I said, now we can do eye tracking and head tracking and so on. So this provides extremely valuable information for us doctors who try to understand, what can we do for these patients who have vision problems, and how these patients with vision problems perform in their daily life. And so I believe, this is really the future, and we will need more and more people able to code, able to troubleshoot. Danielle was mentioning that previously also. I mean, the troubleshooting part is very important also. So yeah, I think that's the future, and I hope some of you, a brilliant student, passionate by coding and so on, would join us in a few years to really expand that field. All right, thank you very much, everyone. Thank you for listening. I'm happy to discuss and answer any of your questions.
Yes, thank you so much, Michael. And thank you for the shout. I wasn't expecting you to show me in that slide, but I'll take this as an opportunity to say that in 2021, when I was putting together the idea of the SRHacks competition, it stemmed from my experience working in Michael's lab and looking back at what developing skills in engineering and programming opened a lot of doors for me. And I wanted to also provide students like yourselves an early gateway into developing these skills, because I know it can be daunting at the beginning and you kind of don't know really where to start. So I hope that through this competition, it helps you guys or inspires you guys to follow in these careers, or helps you in some way down the line. So with that said, I will we'll get into some questions that we have here for you, Michael. So I guess the first one, just because for some of the students this might be new, are any other scientists and doctors using these same game engines to perform their own work as well?
So, I mean, this exact same game is only used by us, basically, but there are other games out there that are developed by doctors, also using VR. VR is originally was very much used for motor rehabilitation. You know, if you wear the haptic glove, and then you create this virtual environment around you, and you can, like, you know, grasp objects and reach out to objects. That was done originally for people and participants who had strokes. So often when you have a stroke, this means that you have some sort of bleeding in your brain, or a vessel or an artery which is stuck. So this has, I mean, like, dramatic consequences on your brain and how your brain functions. And often your vision is affected, but also, you know, your motricity, your ability to grasp things, to move, and so on. And so one of the rehabilitation and the main rehabilitation is, again, to stimulate the motor function. When we call motor function, means, you know, are you able to, again, grasp a glass, or you know, take a pen and write, and so on and so on. And this was essentially done, I mean, now it's done using VR and haptic gloves, because this helps participants to work again and train again their handling and moving their fingers and so on. So, I mean, what I presented, we are the only ones using it. But as I said, I mean, there are other programs or other applications that are out there by other researchers using other devices. And there is not only the Oculus, I mean, there are other brands of VR out there. So it all depends on what you want to do, how you want to do it. I mean, what we love in these particular headsets is that they are standalone. So this gave us a chance to provide it to the participant. You don't need to hook it to a computer for it to work. So that's really great.
Awesome. Thank you. I guess a follow-up to that would be in your opinion, how important is it nowadays to develop like these programming skills if someone in our audience, for example, wants to work in medicine or in science?
I mean, it's extremely important, because, I mean, there are two aspects, I would say. There is the pure coding aspect, where you create those games, where you create those stimulation procedures, and that's one of them. And there are many others. I did not present some of the other work that we have here, but we have now developed over the years, and Eduardo was part of it, and other type of stimulation, also auditory stimulation, together with visual stimulation, to diagnose or to identify whether or not you have, or participants have, problems in processing speed, for example, and so on and so on. So to me, this is something that it will explode in the coming 5 years or 10 years. So there is one aspect where it's purely design and working on those together with doctors, of course, and together with scientists, because they're going to guide you and tell you, okay, I need something that, you know, is now moving that speed, or is going to do something in that part of the visual field, and this is encoded with it's either a ball or a target, or and so on and so on. It's emitting a 3D sound. I mean, it's like designing a game a little bit. And then there is another part, which is, I would say, maybe less exciting in terms of creativity, but would be essential, I mean, to any progress, is data analysis. And data analysis requires heavy programming in Python and so on to be able to sort the data. And so these jobs are typically the so-called data scientists, and maybe you're aware of these terms. And these are people nowadays, I mean, they are gold on the job market, you know, because they are able to sort out thousands and thousands and thousands of data, of numbers, of tables. And this is crucial because of this high technology. VR now collects a lot of data. For example, and Eduardo knows that, we are collecting eye tracking data. So every 10 milliseconds, you have a coordinate of your eye position. Okay, that's every 10 milliseconds. So you have 100 data in 1 second. Okay, so you count 1 second and you have 100 data points that are corresponding to 3D, three-dimensional coordinates of your eye position in the headset, okay? So where are you tracking, where are your eyes looking in the headset? You have 100 of those each second. Right now, our stimulation lasts 20 seconds. I let you do the math. That's just for one session. So this generates like tons and tons and tons of numbers that are essential for us when we analyze them, but you need to find a way to analyze them efficiently. You're not going to, open your Excel file and go through all those lines. And I think Excel sheets can't even handle that many numbers, So there is really like managing and handling big data. This is the other part, I would say, of all the coding and hacking and coding using Python or other type of platforms to be able to efficiently, reproducibly, and reliably sort heavy loads of data. And that's as I said, I mean, that's the other part of the coding and so on, which is really crucial, because without this, we won't be able to progress. We won't be able to analyze this data. And if we can't analyze them, there is no follow-up, What do we do with that? Can we still improve something in these participants? But if you don't have the data and if you can't analyze it, there you go. You're done with your work. And we don't want that.
No, for sure. And I think one of the questions that people were wondering about is, because you deal with patients with eye disease or that have issues with their eyes, it kind of seems surprising that you would use a headset just because of like the bright lights that are kind of presented to their eyes within the headset. And they're kind of asking, are there any kind of issues with that, or do you take any extra precautions when delivering this type of intervention?
So yeah, that's a great question. And indeed, we take precautions because we know some people might be sensitive to light. So we play on the contrast. One of the games that you saw was on a black background. So when it's a black background with like bright targets, it's easier on the eye than if you have really a white background, let's say. Now, when we add this background to make it more real world, for example, the one I showed you with, and you can see it here on that slide with the intersection of, the real life intersection in Toronto, we every time make sure that, in terms of luminosity and contrast, this can't damage the eye, because, and it also, depends on the type of participants. When you know that your population of interest, or this particular study is now including a certain type of population that is sensitive to high contrast or to bright light and so on, we take we are precautious, and we make sure that this is not harming or making things worse, I would say.
And just to one last question to end off the presentation, just given the unique nature of your work with virtual reality and using a game engine to create tools, rehabilitation tools for patients, do you think like maybe in the future there will be, I guess, like a category of specialized video games specifically made to help people with disease to either improve or maintain their health? What's your thoughts on that?
Well, this could likely be something that will happen, that you turn what the stimulation that we are doing now, which I agree for people who are used to play games are quite annoying. But we first need to identify, what is good for your vision. Is it the fact that you are tracking one ball or multiple balls? Is it the fact that they are yellow or they are orange or they're red? So we need to identify which features are important, the speed of the movement, how how much of the visual field is the movement covering, and where in the visual field you are stimulating your vision. These are important parameters that we first need to figure out. And once we understand a little bit better how this works, what can be beneficial to patients, this can be turned into games, definitely. And then this would make it much more fun to use and play. I agree. I mean, and we just finished a study with children who have this disease that I showed you, which is called hemianopsia. So they are missing part of the visual field. And we just finished a study with 10 of these participants, which were aged 12 to 17. One of their complaints was that the game is boring. And I clearly hear that and I can understand that. But as I said, that's the beginning. We need to identify what's good, what is beneficial over time, and then we can transform or integrate it into a games. But right now, I can't say, oh yeah, just go play games and your vision will be better. I can't say that because I don't know yet exactly what is beneficial for your vision over time.
So I think that's important to say, because I guess during this time, while Dr. Reber and everybody else involved does the boring stuff, by the time you guys are ready to enter the job market, you guys will be dealing with the fun stuff, which will be integrating the game stuff and making these tests hopefully something really cool and meaningful. Okay. Thank you so much, Dr. Reber, for attending and giving your presentation. It's always
thank
a
you
pleasure.
for inviting me. I hope you guys enjoyed.
Yeah, thank you. And we'll, again, for people that weren't able to make it, we will be recording this and making this available to everyone. So thank you everybody for watching, and I look forward to seeing what projects you guys have at the deadline later this next week. Okay, have a great weekend, everyone.
Have a great weekend. Thank you, everyone.